The first question we are often asked by our customers is, why should I choose a zirconia phase? In this brief overview, we will discuss the two main reasons our customers choose zirconia-based columns for their most difficult separations. The first and most critical reason to choose a ZirChrom phase is selectivity. ZirChrom phases have a very different surface chemistry when compared to silica, allowing for unique and oftentimes superior selectivity. The second most cited reason ZirChrom users choose zirconia is the unparalleled stability of zirconia-based phases. The superior chemical and thermal stability of ZirChrom phases enable a larger range of method development tools and shorter runtimes. There are three main tools available to effect the separation in traditional reverse phase method development: stationary phase, organic modifier type, and organic modifier percentage. While all three of these options are available on zirconia-based phases, the unique surface chemistry of zirconia allows for some additions to the method development toolbox. Selectivity can be adjusted using buffer type as well as buffer concentration. The stability of the phase allows for the use of the entire pH range for 1 to 14, as well as temperatures of up to 200 degrees Celsius with our carbon-clad zirconia phases. While this overview will present a case study to cover these topics in general for all zirconia-based phases, additional Chrom-U presentations detailing the chemistry and use of our most popular phases can be found on the Chrom-U page of the ZirChrom website. All ZirChrom phases are based on a zirconia particle. The crystalline structure of the zirconia particle has 7 bond valency when compared to silica's 4. The additional bonds in the crystalline structure of zirconia protect the structure from hydrolysis. The result of this configuration is a particle with superior stability and a unique surface chemistry. The surface of zirconia has 3 types of sites, all highly reproducible and homogeneous. There are Bronsted acid sites, Bronsted base sites, and a large population of Lewis acid sites on the surface of zirconia. The Lewis acid sites on zirconia provide a platform for ligand exchange interactions. If the buffer chosen for the analysis contains a Lewis base, that buffer will interact with the surface of zirconia. These ligand exchange interactions allow for temporary dynamic modification of the surface of zirconia. Lewis base buffers will interact with the zirconia surface according to the heliotropic scale shown here. Through this modification, the user can actually modify the net surface charge of the zirconia particle. Strong Lewis base buffers, high on the heliotropic scale, such as phosphate, impart a very large net negative charge on the surface, and the weak Lewis bases, lower on the scale, such as chloride, impart little or no net negative charge. These 3 figures detail the net surface charge throughout the pH range of A. Zirconia without Lewis base buffer, B. Zirconia with a strong Lewis base buffer, and C. The silica surface. While we show the entire pH range for the silica surface within its practical pH range of 2 to 8, the surface is slightly net negative. In comparison, the zirconia surface, without any Lewis base buffer in the mobile phase, is slightly positive at low pH, neutral at neutral pH, and negative at high pH. If we then add a very strong Lewis base buffer, such as phosphate, we can see that the net surface charge throughout the pH range is negative, ranging from slightly net negative at low pH to very negative at high pH. In fact, at high pH, the net negative charge on the surface of zirconia is a factor of 4 larger than of silica at any pH. The higher the buffer is on the heliotropic scale, the larger the amount of charge imparted on the surface of zirconia. Thus, the amount of negative charge on the surface of zirconia can be controlled both by the strength of the Lewis base buffer and the pH of the separation. For this overview, we present a case study examining the behavior of 6 amine pharmaceuticals under varying conditions on our ZirChrom PBD phase. In this slide, we examine the effect of Lewis base buffer type on the retention of these basic compounds at a neutral pH. The buffers range in strength from the top chromatogram acetate a very weak Lewis base, to the bottom, phosphate, a very strong Lewis base. We can see very clearly in these chromatograms the effect changing the buffer type, and thus the surface charge, has on the selectivity of the phase. With acetate, we observe a primarily reverse phase separation and inadequate resolution of the compounds. With fluoride, we see the retention increase, suggesting ion exchange has now been added to the modes of retention. Finally, with phosphate, we see the retention of these positively charged molecules increase further, with the predominant mode of separation now being ion exchange, resulting in good peak shape and excellent resolution of all compounds, including the closely related amitriptyline and nortriptyline, designated 5 and 6 in these chromatograms. As the predominant mode of separation is now ion exchange, the separation can then be further refined or tuned by adjusting the ionic strength of the mobile phase. Here, in the top chromatogram, we show the 20 millimolar phosphate condition from the previous slide, and in the bottom chromatogram, we increase the ionic strength to 100 millimolar phosphate. By increasing the ionic strength of the mobile phase, we decrease the ion exchange component of retention of these positively charged molecules, effectively returning the predominant mode of separation to reverse phase. While we show extremes in this example, this data clearly demonstrates how buffer type and concentration can be used to tune in the ideal selectivity. In this slide, we examine the effect of pH on selectivity using the same 6 basic pharmaceuticals and our ZirChrom PBD column with phosphate in the mobile phase. Beginning with the best condition from the previous slide, pH 7.5, we have a good separation dominated by ion exchange. If we then lower the pH to 4, thus lowering the net negative charge on the surface of zirconia, we see, as expected, that the retention of the compounds has for the most part decreased, as the prevalent mode of retention is returned to reverse phase. However, if we raise the pH to 9.5, we observe some interesting phenomena. The retention, despite the still increasing net negative surface charge, goes down. This is due to the analytes reaching pHs of near or above their pKa, moving from a net positive analyte charge to a net neutral charge. If we take the pH even higher, to 12, we see that all of the analytes are now neutral, and we have a greatly altered elution order with a primarily reverse phase separation. Again, these examples are extreme, but clearly demonstrate that buffer type, concentration, and pH can be dynamic and powerful method development tools on a zirconia-based phase. In the first half of this overview, we have discussed the unique surface chemistry of zirconia and how it can be utilized to maximize your method development toolbox. In the final half of the presentation, we will briefly discuss the chemical and thermal stability of zirconia. In this high pH stability comparison, we have selected a range of modified high pH compatible silica-based phases to compare to our ZirChrom PBD phase, shown in red, and our diamond bond C18 phase, shown in green. Each column was exposed to a solution of 50 millimolar potassium phosphate buffer that had been adjusted to a high pH selected to be within the column's recommended pH range. To quantify any degradation in column lifetime, periodic injections of a standard were made and retention graph versus column volumes of high pH exposure. Although the high pH stable silica-based phases do perform much better than traditional silica, the data clearly demonstrates that even the most robust silica-based phase has only about a 5,000 column volume lifetime. In comparison, the testing of the zirconia-based phases was discontinued after no appreciable change in retention could be detected after an exposure of more than 14,000 column volumes. The increased thermal stability of zirconia allows for the use of elevated temperature as a method development tool. Elevated method temperature decreases mobile phase viscosity and improves mass transfer, allowing the user to increase the flow rate and thus the speed of separation without switching out columns or having to acquire expensive specialized equipment. Alternatively, higher temperatures can be used while holding the flow rate constant to reduce the organic content of your mobile phase. A more detailed Chrom-U presentation on the practical implementation of high temperature can be found on the Chrom-U page of the ZirChrom website. In this overview, we have touched briefly on the two main reasons our customers choose ZirChrom phases for their most difficult separations: selectivity and stability. The unique selectivity and unparalleled stability of ZirChrom phases add new tools to your method development toolbox, allowing you to develop methods that best suit your compounds rather than the limitations of the stationary phase. Newsletters with additional information about the unique multimodal selectivity of ZirChrom phases and additional case study can be found on the Chrom-U page of the ZirChrom website. Thank you for completing this Chrom-U webinar. On the ZirChrom website, you can access our full Chrom-U webinar series, use our free Buffer Wizard tool, or learn more about ZirChrom products and applications.